All right, we're back with part 2 of lesson 2 in module 12. So when I left you in part 1, I gave you a little bit of a homework assignment to write down a question and told you we would go through the answer when we got back. So here is the example problem. So if you have not done this yet, go ahead and pause the video and see if you can complete this based off of the information we learned in part 1. Otherwise, here we go. Let's see what we get for our answer. Not sure if that's running, so there we go. All right, so we have to determine the mass in grams of a party balloon. And so here is our given information. We're going to use PV equals nRT, so our ideal gas law, but we're going to substitute mass over molar mass for our moles so that we can isolate the mass. So the actual mass of the gas in this balloon would be 0.454 grams. Note that we use the molar mass of helium that we get off the periodic table over here. All of our units are in atmospheres, liters. We're using grams per mole and then grams here, so those would equal out to moles. And then we have Kelvin over here. Okay. All right, so moving forward, next order of business we're going to talk about is the ideal gas law and its relation to density. So I'm going to start with our modified ideal gas law. So PV equals mass over molar mass times RT. I see the sun is setting, so my lighting is getting all messed up now. But I'm going to go ahead and rearrange this. I'm going to move volume over so that we have mass over volume. And mass over volume is density. So that means density does actually appear in the ideal gas law. So we can have P is equal to density times RT over M, or capital M, which is capital M is the molar mass. Okay, so I should have probably mentioned that or pointed that out in part 1, but lowercase m is mass, so the actual mass of the gas, and capital M represents the molar mass of that gas. So here we have another modified version of the ideal gas law that we could use to work with density. Okay, so now I have another example problem here. Go ahead and pause the video, see if you can use that information to solve the problem. Here's your given information. Okay, so hopefully you were able to solve this problem. And moment here, we should see the solution pop up on the screen. And so we can see that our, get me out of the way here. We can see that we used our modified version and solved it for molar mass, because if we solve for molar mass, we can identify gases using molar masses. So we got 28 grams per mole. Please note that this is a diatomic gas. So diatomic means it has 2 atoms. So here is a list of our diatomic elements. And we're looking for the one that would have a molar mass of 28. And that would be nitrogen in this case. Because nitrogen, just a nitrogen atom, is 14 on the periodic table. But since we have 2 of them, that would be 28. So this gas is, in fact, nitrogen gas. Okay, so we're going to jump back to the slideshow here in just a second, and we're going to finish this unit or this lesson off with talking about real gases versus ideal gases. All right, back in a moment. All right, we're back here in the slideshow, and I'm going to go ahead and finish this lesson off talking about real versus ideal gases. So we talked about the ideal gas law, and the ideal gas law is assuming that gases act ideally, and the ideal gases use all the assumptions that kinetic molecular theory assumes, or all the assumptions that kinetic molecular theory uses. So those are things like the particles take up no space, they have no intermolecular attraction, so intermolecular forces. There's no attraction or repulsion between the gas particles themselves. They're in constant random motion, and that when they collide, there's no energy lost. Those are all assumptions made in the kinetic molecular theory model that the ideal gases use. well, it turns out that this is not what happens. Okay, so real gases are not ideal. Okay, now for the most part, most gases actually do, most temperatures and pressures, gases actually do follow the ideal model pretty well. But all gas particles have some sort of volume. They are matter, and so all matter has mass and takes up space. So they do have volume. They do have intermolecular forces. There are going to be at least London dispersion forces between them, but there might be dipole-dipole, or there might also be some hydrogen bonding going on. So there are a little bit of attraction between the particles, and when the particles do collide, there is going to be some energy lost. They're not perfectly elastic, but like I said before, most gases at most temperatures and pressures will actually follow the ideal gas law pretty close. I mean, you got to be measuring pretty accurately in order to see the difference. Okay, under extreme pressures is where we'll see the deviation from the ideal gas law. And so if you think about this, if you have really super high pressure, okay, these gases will probably interact more, and we're going to see more deviation. If we have low temperatures, those particles are moving very slowly. Okay, and so I like to use the analogy of, like, let's say that in order for a particle to interact with another particle, they have to first meet each other, right? And if you're running past each other, you're probably not really going to meet each other. You're just going to go right past them. But if you're walking past somebody, you might end up stopping and talking, saying hi, how you doing, how's your day? You're more likely to do that than if you're just running down the hallway. Unless, of course, you're running past Mr. Y and he stops you in the hallway. And then the polarity of particles is going to matter, because the more polar the particles are, the more attractive they're going to be towards each other. And also the size. So bigger particles have bigger London dispersion forces, and so they're going to attract each other more as well. So that's kind of a rundown on the difference between real and ideal gases. Let's go ahead and check our knowledge. So what is the volume of 1 mole of gas at STP? So you should recognize that as our molar volume. It's going to be 22.4 liters. And it doesn't matter what gas it is, any ideal gas, 22.4 liters per mole. Which is not an assumption followed by the ideal gas. Again, if you need more time, go ahead and pause. Okay, so we assume that the collisions are elastic, not inelastic. When is the ideal gas law more likely to work? Alrighty, here we go. Again, if you need more time, pause the video. When does the ideal gas law not work? Sorry, most likely to work. That's going to be when the gas particles are nonpolar. Because remember, if they're polar, they're going to attract each other, and we've got those attractions going on that we assume aren't happening. And then also at extreme high pressures and temperature, or extreme high pressures and low temperatures, is when the ideal gas law falls apart. All right, that concludes our lesson 2. So we will see you back for lesson 3 in a bit.